Log on, tune in, find out. Another good idea from Cambridge.
Makarychev will talk about Vertex Sparsifiers and Lipschitz Extendability.
Thank you for the introduction and thank you for inviting me to this program. So I will talk about Vertex Sparsifiers and Lipschitz Extendability, and this is joint work with Konstantin Makarychev. So let me first describe the notion. So first I want to define Vertex Sparsifiers and in general talk about the notion of sparsification. Then I will describe the motivation to study Vertex Sparsifiers, the definition of Vertex Sparsifiers, and show some applications of this notion. I will describe known results, and then I will talk about seemingly unrelated topic of Lipschitz extendability, but we will see that in fact these two areas are very closely related. And finally I will talk about some proofs, though I won't be able to talk about proofs in much detail. Finally I will conclude with some open problems. So what is graph sparsification? Suppose that we have a very large graph G. Say, think of this graph, this is the internet graph. The vertices of this graph are all computers, and two vertices are connected with an edge if these two computers are connected with a link. And our goal is to find a simpler graph H, which in some sense is similar to the graph G. Why we are interested in this problem? Because graph H, in a sense, is a compact representation of the graph G. To store the graph H, we need much less space, and then if we want to solve a problem on the graph G, we can solve it instead on the graph H. Since H is much smaller, the running time will be much less. And similarly, if we solve combinatorial optimization problems on the graph H, on the graph G, we can instead solve them on the graph H, and since the graph H is much smaller, we will get better approximation ratios. Of course, what I described here is not a definition. There are many ways to define this notion of simpler, and there are many ways to define the notion of similar. So it's not clear in which sense the graph H is simpler and what it means that H is similar to G. And in fact, several different notions of sparsification were studied in the literature. So the most popular ones are the notions of combinatorial edge sparsification that were introduced by Benzer and Karger in 90s, and the notion of spectral edge sparsification that was introduced by Spielman and Tang around 10 years ago. In this talk, we will talk about a different notion that was just introduced 2 years ago, at first by Moitra and then by Leighton and Moitra. So let's look at the following problem. Suppose that we are given a large computer network G. For example, think of this network as the internet graph. And we have several computers in this network. So for example, if we are a company, then we can have several offices in different parts of the world, and we can have computers in these offices. So what is important here that the network can be very large. So it can contain billions of computers, but the number of computers that we control is much smaller, maybe it's hundreds of computers. And we call these computers terminals, and we denote the set of terminals by U. So U is much smaller than the size of G. We are also given the capacities of edges of the graph, or the data transmission rates for every link. And suppose that every terminal SI, every computer SI wants to send DI bytes of data to terminal TI. We are interested how much time we need to send all the data. Note that all transmissions are not independent. For example, if in this example, if S1 wants to send some data to T1 and S2 wants to send some data to T2, then both of them need to use this link in the network, right? So this link might be the bottleneck in this problem, and it will determine the transmission speed of this link will determine the required time. In general, of course, the graph is not a tree, and the entire network can be very complex. It's not a tree, it's not a bipartite graph, it can be an arbitrary, very complicated graph. So what is known about this problem? We can solve this problem efficiently, and we can find the optimal time, we can find the optimal routing, but in order to do that, we need to examine the whole network with billions of nodes. And in a typical situation, if we have these computers, we will solve this problem over and over every time we need to send data. So we will solve this problem with different sets of demands. Today, a certain pairs of computers want to exchange some data, and tomorrow, other pairs of terminals from the same set of terminals will want to exchange some data. So our goal is to find a virtual private network on the set of terminals, which in some sense is equivalent to the entire network. So we want to find a graph on the set of terminals which is equivalent to the original graph. And this was formalized, and this notion was proposed by Leighton and Moitra, who gave the following formal definition. We say that a graph H is a vertex loss Sparsifier of quality Q for the graph G if for every set of transmission demands di, the optimal transmission time th is within a factor of q of the optimal transmission time for the graph G. So we have this inequality. Note that transmission times depend on the demands di, and we require that this inequality holds for every set of demands di, but the graph H does not depend on this demands di. H depends only on the graph G and on the set of terminals U. In this so this is the notion of vertex flow Sparsifier, but in this talk we will mostly deal with another notion, the related notion, the notion of vertex cut Sparsifier. Let me define it. And now it's a little bit simpler. So suppose that we have this graph G, and this is the set of terminals U. Now consider a set of terminals, subset of terminals S. For example, these two vertices belong to this subset S. Consider the minimal cost cut in the whole graph that separates these two vertices from U minus S. So these two vertices from these two vertices. In this example, this cut consists of these two edges. So these two edges form a bottleneck. So they separate this part of the network from this part of the network. And another example, for example, if the vertex, if the set S consists of this vertex, then S minus U consists of these three vertices, and in this case, the bottleneck consists of these two edges. And a vertex cut Sparsifier is a subgraph, a vertex cut Sparsifier is a graph on the set of terminals such that the size of every cut, so no matter how we choose the set S, subset S of terminals, the size of the cut between S and U minus S in H, so the number of, in this example, of these orange edges that the cut cuts, is approximately equal to the size of the bottleneck cut that separates this set from the complement in the graph G. let me repeat this definition. So we are given a graph G with on the set of vertices V. Every edge has cost alpha ij, and we say that H is a Q-quality cut specifier for G if for every partition of terminals into two sets S and U minus S, the cost of the minimum cost cut that separates S and U minus S in G with respect to weight alpha ij, and the cost of the cut that separates S and U minus S in H with respect to this new weights beta ij are within a factor of Q. Is this definition clear? So this will be the main definition. Cut?
Like in the four Ferguson model?
Yes, it's like so we partition the graph into two pieces and we look at the set of edges that go from one piece to the other. So these two definitions, the definition of vertex cut specifiers and the definition of vertex flow specifiers, are closely connected. In fact, every flow specifier is also a cut specifier, but not necessarily the other way around. And we want to find sparsifiers with quality Q as small as possible. Ideally, we want Q to be equal to 1. In this case, just the size of the cut in H is exactly equal to the size of the cut in G, so this will be the ideal case, but unfortunately, we won't be able to guarantee that always. But anyway, our goal is to find the optimal dependence of Q on the size, on the number of terminals K. So throughout this talk, I will denote the whole graph by G, the set of terminals by V. Alpha will be the cost of edges in the graph G. I will denote the sparsifier by H, and N will be the total number of vertices, K will be the number of terminals. And we will assume that K is much smaller than N. This is the most interesting case. So why are we interested in sparsifiers? As I mentioned, first was just a sparsifier is a compact representation of the graph. For example, if the graph is the internet graph, then N is equal to several billions, and if we have only 100 computers, then say K is equal to 100. So just to store the representation of the graph, we need much less memory. Then the algorithms for repeated tasks will run much faster on our small graph. And finally, perhaps the most important application is that it's very useful for designing approximation algorithms. The approximation guarantee of many algorithms depends on the size of the graph. And say the approximation guarantee for the sparsest cut problem is roughly square root log n, where n is the number of vertices. But if we are only interested in terminals, in some sense, then we can, using sparsifiers, reduce significantly improve the approximation factor by reducing the size of the graph. This notion of vertex sparsification was introduced 2 years ago at first by Moitra and then by Layton and Moitra, but since then it attracted a lot of attention, and independently with our works, 2 other groups of people obtained somewhat similar results. So the first one was Charikal, Layton, Lai, and Moitra, and the second one was Engler, Gupta, Kraus, Gamer, Talgam, and Talwar. Let me now describe what was known about vertex sparsification. So Moitra and Layton and Moitra proved that there always exist flow and cut sparsifiers of quality log k over log k. But this result was purely existential. So they didn't show how to find sparsifiers of this quality efficiently. They showed, however, how to find sparsifiers of quality, roughly speaking, log squared k efficiently. On the negative side, they proved a lower bound, a constant lower bound for the quality of cut sparsifiers, and they proved a lower bound of log k for the quality of flow sparsifiers. And the main open questions were, first of all, to prove an algorithmic upper bound that matches the existential upper bound, so prove an algorithmic upper bound of log k over log k, and then improve the lower bounds, say improve this constant to a function that tends to infinity, and ideally to improve this existential upper bound if it is possible. And our main results, first of all, we define a notion of matrix sparsifiers. Matrix sparsifiers is just another definition of flow sparsifiers, but it's more convenient and it's much easier to work with them, at least in our opinion, and it can be generalized in several ways. Then we prove the algorithmic upper bound of log k over log k, and finally we establish a direct connection between vertex sparsification and Lipschitz extendability. So I will denote Lipschitz extension constants in a minute, but what we prove that the quality of cut sparsifiers, the optimal quality of cut sparsifiers, is exactly equal to the Lipschitz extension constant from L1 to L1, and the quality of flow sparsifiers is exactly equal to the Lipschitz extension function constant from L infinity to this space, which is just L1's sum of L infinity spaces. What is interesting here that these equalities are exact, so it's not just that these quantities are approximately equal, they are exactly equal.
Show me what is the symbol 1?
This?
Yeah, no, the sum is but 1.
So this space is like every element of this space is a tuple of points x1, etc., xr. Each xi belongs to L infinity, and the norm of this of this point is equal to the sum of the norms of xi's, L infinity norms of xi's. And here we take just the sum, and this is why denoted by a plus with the lower index 1. Now, using some standard techniques, so using the method of Johnson-Lindström's, and who showed the connection between Lipschitz extendability constant and projection constant, and using lower bounds on projection constant by Greenbaum, we proved the lower bound of square root log k over log k for the Lipschitz extension constant from L infinity to this space, and this gave us the square root log k over log k lower bound for the quality of flow sparsifiers. And using a similar approach, a little bit more involved approach, we got this lower bound on the quality of cut sparsifiers. Interestingly, Charikar, Layton, Lee, and Moitri independently and using completely different techniques got this lower bound on the quality of cut sparsifiers. So at a certain point, we even thought that this might be the correct answer. But after we published a preliminary version of our paper, Johnson and Schachman actually told us that their result with Fiegel actually implies this lower bound on the quality of cut Sparsifiers. Let me now define what these Lipschitz extension constants are. So suppose that we have two metric spaces x and y. Moreover, we will assume that y is a Banach space. So we say that the Lipschitz extension constant ek from x to y is a minimum ek such that every map f from a key point subset of x to y can be extended to a map from the whole space x to y with a Lipschitz constant at most, this Lipschitz extension constant times the Lipschitz norm of f. Is this clear? For example, consider the case of just real valued functions, and here x is not necessarily a one-dimensional space, but I draw it just as a line. We have a function f, which is defined on a subset x prime. Then the Mark-Chain theorem says that we can extend it to the function on the whole space x so that the Lipschitz norm of f doesn't increase. And this, in other words, this means that the Lipschitz extension constant from any metric space to R is equal to 1. Similarly, the Kirsch-Brown theorem says that the Lipschitz extension constant from L2 to L2 is also equal to 1. In general, however, the Lipschitz extension constant is sometimes greater than 1, and here is a simple example. Consider, let's compute a lower bound on the Lipschitz extension constant from L1 to L2, and consider 3 points in L1, 1, 0, 0, 0, 1, 0, and 0, 0, 1. The distance between any two of them is equal to 2, and we can map them to the vertices of this triangle with this side length equal to 2. So this is an isometric embedding of these 3 points into Euclidean plane. And now we want to extend this map to the fourth point D with coordinates 0, 0, and 0. It's easy to see that the best choice for this point is the center of this triangle. However, the distance from this point to any of these points is equal to 1. And the distance from the center of the triangle to the vertices of the triangle is equal to the square root of 3. So we have to increase the distance from 1 to square root of 3. The notion of Lipschitz extendability was first studied in math, so the first works date back to 1930s, and recently it attracted attention of computer scientists, so there were several applications of this notion in computer science. And what we proved that the quality of cut Sparsifiers is equal to the Lipschitz extension constant from L1 to L1, and the quality of floor Sparsifiers or metric Sparsifiers is equal to the Lipschitz extension constant from L infinity to this space, and in particular it is greater or equal to the Lipschitz extension constant from L infinity to L1. So let me briefly summarize our results. So first of all, we give an algorithmic upper bound of log k over log k, we give better bounds for some special families of graphs. For example, if we know that the graph has a bounded genus, we can get much better bound. Say if the graph is planar, or we can draw it on a torus. We obtain these lower bounds on the quality of low and cut Sparsifiers. And finally, we show that if a certain conjecture of ball is true, then there exists an existential upper bound of square root log k for the quality of cut Sparsifiers. So in 1991, Ball asked whether the Lipschitz extension constant from L2 to L1 is bounded by some absolute constant. If this conjecture is true, then we can improve the upper bound. On the other hand, in order to improve our lower bound, we have to disprove this conjecture. So it turns out that this conjecture is very important for our problem. Let me now very briefly describe our approach and present some proofs. So recall the definition of cut Sparsifiers. So we say that the graph H on the set of vertices Q is a cut Sparsifier for the graph G if for every cut S the cost of the cut S, and I will denote it as follows. So I will write it as a beta of delta S, where, sorry, I will denote it, so I will denote the cost of the cut with respect to weights alpha as alpha of delta of t, and I will denote the cost of the cut, this cut delta S, as beta of delta S. So what does it mean? If we have a graph and a cut in it, so we have a cut S u minus S, then we can consider the corresponding cut metric. So the distance between 2 points x and y is equal to 1 if x and y belong to one part, so if either both of them lie in S or both of them lie in, oh, I'm sorry,
Equal to 0.
is equal to 0 if both of them lie in S or both of them lie in u minus S, and it is equal to 1 if x belongs to S and y belongs to u minus S, or x belongs to u minus S and y belongs to S, right? So these distances are equal to 1, and distances inside the set are equal to 0. Then the cost of the cut can be written just as a sum over all ages ij. Alpha ij is the cost of the h times the distance between I and j with respect to the cut metric. If I and j lie in one part, then this term doesn't contribute anything, and if I and j lie on the different sides of the cut, then this is equal to 1, so this term contributes the cost of the h. And similarly, we can write the cost of the cut in the graph h as beta of delta S. Note that both these two functions are linear functions as a functions of these elements delta of ij. So our goal, h is a cut Sparsifier if for every cut S and the minimum cost cut t that extends the cut S to the whole graph G, this inequality holds. But we can generalize this inequality. We can require that not only this inequality holds for cut metrics, but it also holds for any metric on the set of terminals U. And this will be a Stroner condition. So let's say that the graph H is a metric specifier if for every metric du and the minimum cost extension dv of this metric to the whole graph G, this inequality holds, where this minimum cost extension dv is the metric on the whole graph G that coincides with the metric du on the set U, and that minimizes this objective function alpha of dv. So this notion is stronger than the notion of cut sparsification, right? Because we require that this inequality holds not only for cut metrics but for all metrics on the set H. In fact, we prove that the notion of metric sparsification is the same as the notion of flow sparsification. But I don't prove this today. So now let's look at our problem geometrically. Here I plot the cost of the minimum cost extension of a metric. So this axis is actually not one-dimensional, so I draw it I draw this picture as a two-dimensional picture, but it should be a multi-dimensional picture. This axis, this point, denotes a metric on U. Or in other words, you can think of this as a vector whose components are just pairwise distances between points in U. And this graph is the cost of the minimum cost extension of this metric du to the whole graph. So in other words, the minimum cost extension of du is the cost of the metric dv that extends du to the whole graph G and whose cost is minimal. It's not hard to see that the graph of this function is convex. Now, our goal is to find a set of weights beta such that beta of du approximates this graph. So we want this inequality to hold, and in fact beta is a linear function, right? So in other words, we want to find a plane, a linear function that approximates this graph. So we want to find this linear function that lies above the graph of the minimum extension graph and below q times the minimum extension graph. But of course, since this is a hyperplane, if it lies above this graph, then it must also lie above the convex closure of this graph, above this convex closure, right? And what is the best possible value of q? The best possible value of q is attained when this graph touches the convex closure, right? So if q is very large, then these two bodies are far away from each other. Then when we start to decrease q, they become closer and closer to each other, and finally then they touch each other. And this is the best possible value of q. And then we can find this plane that separates them. There is one technicality that we actually require that all coefficients of these linear functions are positive, but in fact we can ensure it, and I don't pay attention to that. So our goal now is to bound the maximum ratio between the y coordinate of this point and the y coordinate of this point. And this maximum ratio is equal to the quality of matrix Sparsifiers. And we can do that actually by using a special type of extension called zero extensions. So I won't talk in detail about zero extensions, but this is a type of extension that we studied in computer science before, and in fact people consider this minimum extension as LP relaxation for zero extension, and it is known that the ratio between the cost of the minimum zero extension and the minimum extension of a metric is at most log k over log k. So this shows that there always exist Sparsifiers of quality log k over log k. Now let's try to find such a Sparsifier. So how can we proceed? One approach is the following. We try one linear function, one hyperplane, and try to find an intersection with this body or with this body. If we find an intersection with this body, then we find a hyperplane that is sort of below this hyperplane. If this hyperplane intersects the first body, then we look for a hyperplane that is above this hyperplane, and finally we find a hyperplane that separates these two bodies. More formally, we use the ellipsoid method, and the ellipsoid method says us which body the hyperplane intersects and in which direction we should move the hyperplane. But there is a problem. We can test the intersection of a hyperplane with this body, but unfortunately we cannot test whether hyperplane crosses this boundary, because it is NP hard to compute the minimum zero extension. So this approach doesn't give us an efficient algorithm. Instead, we use a slightly different approach. So what was our objective? Our objective was to approximate the cost of the minimum cost metric extension by a linear function. Instead, we can try to do something stronger. We can try to approximate the minimum extension itself by a linear function. So you find our goal is to find a linear operator from the set of matrix U on the set U to the set of matrix on V, such that the combination of this linear operator and the function alpha is well approximates the combination of the minimum extension operator and alpha. And of course, if this is a linear operator, then the composition of alpha and this linear operator will be a linear function that well approximates the desired function. So let me explain what it is. So our goal is to find this linear operator phi for every pair of vertices I and j. Phi of j of du is a metric on this graph G, so this must be a metric, and we require that it has good quality. So the operator phi maps every metric du to a metric dv that extends du, and we require that the cost of this metric is at most q times the cost of the minimum extension of du. Of course, since phi of du is some extension, it cannot be cheaper than the cost of the minimum extension. So this inequality always holds. And using similar techniques to what I described, we show that there always exists a metric extension operator of quality log k over log k. Again, our proof is not algorithmic, so it's just a pure existential proof. But unlike the previous case, it turns out that we can actually find the optimal metric extension operator phi. And roughly speaking, we use linear programming. We introduce these numbers for the coordinates of our operator, and then we use this operation oracle to test that our operator always maps a metric on U to a metric on V that extends the regional metric. So I briefly described how our algorithm works, and I want to briefly describe the connection between Sparsifiers and Lipschitz extension constants. So I will show that the quality of optimal metric Sparsifiers is at most the Lipschitz extension constant from L infinity to this space. This direction is a little bit simpler than the opposite direction, that Q is greater than this Lipschitz extension constant. So recall that we want to show that the ratio between y coordinates of these points is at most this Lipschitz extension constant. If you prove that this ratio is always bounded by this Lipschitz extension constant, then you will prove that the quality of Sparsifiers doesn't exceed this Lipschitz extension constant, right? So consider a point on this vertical line, and since this point belongs to the convex closure of this graph, we can express it as a linear combination of some points on this graph. And let's diu be the x coordinate of these points, so the projection to the horizontal plane. Then this coordinate du is equal to the convex combinations of diu be some weights lambda I that sum up to 1, and the y coordinate is equal to the convex combination of y coordinates of these points with the same weights. And this graph is a graph of the minimum extension function. So the y coordinate of point of the ith point is equal to this number, minimum extension of diu. So we have these two equalities. Now consider the metric space U equipped with metric lambda I times di of U. This is a finite metric space, and as any metric space, it embeds into infinity isometrically. Let phi I be an isometric embedding. Then, by the definition, the distance between the images of 2 points P and Q is equal just to the distance between P and Q with respect to this metric. Now consider, let's sum up all these maps and consider this mapping phi, which is a direct sum of these maps phi I. Then the distance between 2 points P and Q is equal to the sum of distances between p and q with respect to these distance functions. But note that this sum is equal to du. So we get that phi is an isometric embedding of this metric space into this metric space. Now we use the fact that we can extend any map from any metric space to this north space to a larger metric space, so that the Lipschitz constant increases by at more the Lipschitz extension constant. So we construct an extension, a map tilde phi from the metric space on V equipped with a metric dV to the space with Lipschitz norm at most this. And recall that dV was a minimum cost extension of the metric du. So we have this Lipschitz function from V dV to the space, and now we project it on each of the coordinates. So we write that tilde phi is equal to the sum of tilde phi 1, etc., plus tilde phi r. Now, since tilde phi extends phi, each of the coordinate functions also extend the corresponding phi I. So now we define distances. Let tilde duv be equal to the distance between tilde phi of u and tilde phi of v, and let the distance tilde di be the distance between tilde phi I of u and tilde phi I of v. Note that this distance extends the distance function du just because on the set u phi tilde phi coincides with phi, and phi was an isometric embedding of the space u equipped with this distance function to L infinity. And similarly, each of these functions tilde di extends the corresponding function lambda I di of u sub u. So we get that by the definition, the y coordinate of this point is equal to the sum of lambda I alpha of di of v. Now we just proved that tilde di is some extension of lambda I di v. So in particular, this means that alpha of tilde di is at least lambda I alpha of di v, right? Because it is some extension and di v is a minimum cost extension. Now, since alpha is a linear function, this is equal to alpha of tilde d, and just by the definition, it is equal to the following sum. Now, each tilde d dv, again by the definition, is equal to the distance between tilde phi of u and tilde phi of v. And since tilde phi, the Lipschitz extension constant of tilde phi is at most the extension constant, we get that this is at most the Lipschitz extension constant time the distance between u and v with respect to the distance function dv. and now again by linearity, and here using the definition of alpha, we get that this is equal to ek times the cost of dv. So we proved that we proved what we wanted. We proved that the ratio between y coordinates of this point and this point is at most the Lipschitz extension constant. And this concludes the proof. The proof of the lower bound is similar to the proof that I just presented, but it's a little bit more involved, and also the proof for cut Sparsifiers is very similar. So let me summarize what we did. We proved the algorithmic upper bound of log k over log k. We got better bounds for some special families of graphs, in particular for a graph of a bounded genus, and we established the connection between the quality of cut Sparsifiers and Lipschitz extendability, and using this connection we established these two lower bounds. And finally we proved that if the open question of ball has a positive answer, then the following existential upper bound holds. There are still some open questions in the area. First of all, it would be very interesting to find exact bounds on the quality of cut and for Sparsifiers. A related question is to find the integrality gap of the linear programming relaxation for the minimum zero extension problem, and it would be very interesting to answer the open question of ball. Thank you.
Are there any questions?
I have some comments. If you have a cut, then your theory is good. But there are problems that you don't have a cut, that what you want to have is a minimum edge in order to maximize or minimize something. Is this possible to do with your technique?
So this applies only if we have a flow or cut. I mean, if it's a different problem, I mean, maybe something similar can work, but this results to flow problem and to cut problems.
And the other one is the extension of the Ham-Banach theorem, the separation theorem. I didn't understand well what is the stone generalization, because I have
it's not a generalization. It's just sort of the Ham-Banach.
Klee, a person in Waterloo, and myself were looking for a multi-convex set. I mean, I have in game theory there are multi-convex sets, which is you put a point in Rn and you don't have a convexity, but you fix all the point in n-1, and then you have the convexity on the other one. And it is possible to have a separation theorem. I have done everything, but there is a mistake. If somebody wants to have a good paper over there, I can give it to him.
Okay, but let's discuss this after the talk. I think so. Let's thank Yuri again.